In this video, we'll find the formula for the sum from k equals 1 to n of k. We're going to do this two ways, and at the end, we'll do a non-formal proof. Also, don't forget to subscribe and turn on notifications so you don't miss the video. Okay, we're going to call this s of n. So this will be 1 plus 2 plus dot 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 plus n. This could be also written backwards, so this will be n plus the previous term is n minus 1 all the way up to 1. Okay, good. So we can add these terms up so that we get 2s of n on the left-hand side. And the right-hand side, well, let's look at this. This is n plus 1. And then 2 plus n minus 1 is n plus 1, all the way up to the last term, which is n plus 1. How many times do we have n plus 1? So let's look at this. So this goes from 1 to n, means we have n minus 1, and then we have to add another term. So this will just be n times. This is n times. Okay, so if we add something up n times, we just multiply it by n. So we have n times n plus 1. Now we have 2s of n on the left-hand side. And of course, n is an integer, so you're allowed to do this. So s of n is n times n plus 1 all over 2. So that's the first method. The second method, so s of n, so this is 1 plus 2 plus dot 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 plus n. Okay. So let's look at s. So s of 1 is 1. S of 2 is 1 plus 2, which is 3. And s of 3 is 4. Or s of 3 is 6, but we don't need that. Okay. But let's look. So we can add a 0 to the beginning and it doesn't change anything. So now we have s of 0 is 0. Okay, good. So if we want to write this as an array, this can be basically 0, 1, 3, and so on. Just be 6, and then so on. Okay. To get from 0 to 1, you have to add 1. To get from 1 to 3, you have to add 2. From 3 to 6, you have to add 3. So on. Notice the pattern? Okay. So you have to get from 1 to 2, you have to add 1. To get to 2 to 3, you have to add 1. And it'll be the same thing. So 1 all the way. So this will be the first degree. But the problem is, you're adding different things. So now we have the second degree polynomial. Okay, so because it's plus 1, we know it is a second degree polynomial. So that means that, I was going to write a sub n, but it's s of n can be written as a n squared plus b n plus c, because we're adding 1 on the second time always. Okay, we know that s of 0 equals 0, so let's plug that in. So that means 0 on the left-hand side equals, now we're going to plug in n equals 0. So this will be, so this has n's in it, so those would be 0, and then plus c, so it's just c. So c equals 0, that means we can get rid of this. Okay, now let's plug in n equals 1. So we're going to have s of 1 equals 1. This means that 1 equals, now we're plugging n equals 1 into these. So this will just be a plus b, because n is just 1. So let's plug in n equals 2. That means s of 2 is 3, because 1 plus 2 equals 3. Okay, so on the right-hand side, or left-hand side, we'll have 3, and this is equal to n equals 2 now. We plug in. So this will be 4a plus 2b, because we're plugging in n equals 2 into here. 2 squared is 4, and then just 2 is 2. Okay, so now let's multiply the first by negative 2. So now we're going to get negative 2 on the left-hand side equals negative 2a minus 2b. So now we can add these terms up. 3 minus 2 is 1. 4a minus 2a is 2 times a. 2b minus 2b will cancel. Not to be. So we can divide by 2, so that means a is 1/2. Okay, good. But we know that 1 equals a plus b. So 1/2 plus b is 1, so b is 1/2 also. So that means that s of n will be 1/2 n squared plus 1/2 n. You can factor out an n over 2, then you'll be left with n plus 1. So that is the second way of doing this sum. So now let's do the semi-proof, or the non-formal way, non-formal proof. Okay, so we have the sum from k equals 1 to n of k. So now we want to show that this is equal to n times n plus 1 all over 2. Okay, Now the first step is to plug in n equals 1. So this is like the base case. So base case. Yeah. Okay. So on the left-hand side, you're just going to get 1 and then question mark, but should be equal to. Now we're going to plug in n equals 1 on the right-hand side. So we're going to have 1. 1 plus 1 is 2 all over 2, and this works out because 2 over 2 is defined to be 1. Okay. So now let's suppose that k equals 1 to capital N of k. Now this is equal to, now we're going to plug in capital N for n. So this would be capital N times capital N plus 1 all over 2. So this works. So this is really that n equals capital N. So now for the n equals capital N plus 1 case, so you're going to have the sum from k equals 1 to capital N plus 1 of k. Now we aren't allowed to use the same formula, but we have to use this formula here. Okay, so how are we going to do this? Okay, so we can split this up into the sum from k equals 1 to capital N of k plus capital N plus 1 plugged into k, which is just n plus 1. Okay, so you know what this is because we just supposed it worked. So that's the sum from k equals 1 to capital N of k, and that's this formula. So this will be, I'm just going to say n from now on, times n plus 1 all over 2 plus n plus 1. Okay. Now we can multiply this by 2 over 2, because that's just 1. So we have a common denominator of 2, so we have n. So let's multiply this out. So this is n times n, which is n squared, plus n times 1, which is n, plus, okay, 2n plus 2 is what you get here. So this is 2n plus 2. Okay, so this is n squared plus 3n plus 2 all over 2. But what do you notice about this? This is factorable into n plus 1 times n plus 2 all over 2. And now you can check this is n plus 1 times, now we're going to write this as n plus 1 all over 2. So that basically concludes the proof because the n plus 1 term gives the output of n plus 1 plugged into n, which is n plus 1 times n plus 1 all over 2. And that is the end of the video. Hope you liked it, and thanks for watching.